A neutron star's magnetic field is so powerful that it physically deforms hydrogen atoms into shapes 10 times longer than they are wide. Not metaphorically. Not approximately. The electron orbitals, the quantum probability clouds that give atoms their shape, get stretched into needles by pure magnetic force. That's happening right now, in objects scattered across our galaxy. Let that sink in for a second. The atom is not some rigid thing. It bends. And a magnetic field can do it. Now here's what makes this terrifying in the best possible way. The magnetic field responsible for that is roughly 1 quadrillion times stronger than Earth's magnetic field. Earth's field is already enough to pull iron filings into beautiful patterns. Scale that up 1 quadrillion times and you don't get a bigger version of the same thing. You get something that breaks the rules of chemistry itself. That's what we're actually dealing with. So why should you care? Because neutron stars are not distant curiosities. They are the collapsed cores of stars that used to be alive. Stars bigger than our sun burned for millions of years, then exploded, and what was left behind compressed into an object roughly 20 kilometers across. That's the size of a city. But it still contains more mass than our entire sun. Everything that made that star got crushed into a sphere you could drive across in 20 minutes. And that crushing is where the magnetic field comes from. When a star collapses, it spins faster, the same way a figure skater spins faster when they pull their arms in. That spinning, combined with the movement of charged particles inside, amplifies the original magnetic field by factors that are almost impossible to express in normal language. The result is a magnetar, a specific type of neutron star where the field hits those quadrillion times Earth levels. Here's a concrete comparison so your brain can actually grip this. The strongest magnetic field ever produced in a laboratory lasted a fraction of a second and reached about 2,800 Tesla. It destroyed the equipment that made it. The magnetic field of a magnetar sits around 100 billion Tesla. You're not going to build a machine that touches that. Now here's the physics that breaks your intuition completely. At field strengths above about 4,400,000,000 Tesla, something called magnetic vacuum birefringence kicks in. The vacuum itself, the empty space, starts behaving like a material. Light traveling through that space gets split depending on its polarization, the same way a crystal splits a beam of light into two. Empty space becomes optically active. The vacuum has properties. That is not science fiction. It was confirmed observationally in 2016 when astronomers studied a magnetar called RxJ 1826-3073. If this is blowing your mind, subscribe right now. Every week we go places textbooks are too cautious to take you. But here's the deeper layer. It's not just the vacuum that behaves strangely. Your body would behave strangely too. Fatally strangely. And not in the way you'd expect. Most people imagine magnetic danger as things flying at you. Magnetism is invisible, so we assume it's harmless unless it moves metal. That model is completely wrong at these scales. The human body is mostly water, and water molecules are diamagnetic. They respond to magnetic fields. In a sufficiently strong field, the tiny magnetic moments inside every molecule in your body would be forced to align. The forces pulling different parts of you in different directions would reach levels that would tear apart chemical bonds before you were close enough to feel warmth, before your nervous system had time to register pain. You wouldn't be burned. You wouldn't be crushed by gravity. You would be pulled apart at the molecular level by the field itself. The magnetism would interact with the quantum structure of matter long before your brain could report a sensation. And this matters for something bigger than just the drama of it. Understanding magnetars is directly connected to understanding the strongest force events in the observable universe. On December 27, 2004, a magnetar called SGR 1806-20 released more energy in 0.2 of a second than our Sun releases in 250,000 years. The gamma-ray pulse it sent out measurably ionized Earth's upper atmosphere from 50,000 light-years away. A star on the other side of the galaxy reached across space and changed our planet's chemistry for a moment. That's not a fun fact. That's a data point about what the universe is capable of. Here's what that means going forward. Magnetars are essentially natural laboratories for physics we cannot reproduce on Earth. The conditions inside them test quantum electrodynamics, the theory describing how light and matter interact, at energy scales no particle accelerator will reach for generations, if ever. Every observation of a magnetar pulse is a free experiment run at energies that would cost more than human civilization has ever produced to replicate artificially. There are currently about 30 confirmed magnetars in the Milky Way. Given the size of the galaxy, the real number is probably in the thousands. Most are silent, slowly losing energy, cooling over tens of thousands of years. But occasionally one flares. And when it does, it writes physics equations in light across the universe, and we get to read them with our telescopes. The atom warping, vacuum bending, body dissolving magnetic field of a neutron star is not an edge case. It's the universe showing you what matter actually is when you stop being gentle with it. The rules we learn at human scales are just one page of a much longer book. And magnetars are a chapter that starts with the sentence, "Everything you know about physics still applies here, but the consequences look nothing like what you've seen before." If that's the kind of science you want to keep exploring, subscribe and hit the bell. Next time we go somewhere just as strange. The universe is not waiting for you to be ready.